Welcome, welcome, welcome. For this tutorial, we are going to go through an equilibrium equation. We recently did a lab on this, and we found the equilibrium temperature using this equation. So what I have here is I have a data table with some data numbers that I made up. And you can see I'm mixing together 100 milliliters of hot water with 50 milliliters of cold water. And you can see here that the hot water is cooling down until it reaches 72 degrees, and the cold water heats up until it reaches 72 degrees. And we're going to do the math down here using this equation to show that it is 72, or at least it's going to be close to 72. So we start up here with a negative m. We need the mass of the hot water because this left side is our hot, and this right side is our cold. And so our hot water we had 100 milliliters. So we have, that's our mass, negative 100. C is the specific heat. Specific heat of water is 1. The final temperature, we know it's 72 degrees, but we are solving for that. So we're going to leave that as our variable. And I need the initial temperature. The initial temperature is, for the hot, was right here, 100 degrees. Okay, equals, we're on the cold side. The mass of the cold is 20. Specific heat of water is 1. Once again, the final temperature is 72, but that is what we're solving for, and I need the initial temperature. Oh, I made a mistake. The initial temperature is 20, what I highlighted, and our mass is not 20. Our mass is right up here, 50 milliliters. So we have 50 milliliters times 1. There we go. All right, so I'm going to multiply the ones through, simplify it a little bit. Okay, and now I'm going to distribute. So I'm going to distribute this negative 100 times both of those. And so I get negative 100 TF plus, because it's negative times a negative, 10,000 equals, and I'm going to do the same thing on this side. I'm going to distribute this 50 to both. So I have 50 TF minus 1,000. So now I need to combine like terms. So to combine like terms, I'm going to get the TFs on one side. So that cancels, and I'm going to add 100 TF to both sides. And so I have 10,000 equals 150 TF minus 1,000. I'm going to do the same thing with my numbers. I'm going to combine like terms, combine these numbers, add 1,000 to both sides. And so I get 150 TF equals 11,000. I'm then going to divide both sides by 150. And I put that in a calculator, and I get 73.3 degrees Celsius. And you can see we got 73.3 degrees from the math. And if you actually did this, you would actually get 72 degrees. That's what we got when we demoed it. So there's a difference of 1.3 degrees. So all of this heat did not go to the water, the cold water. If all the heat moved from the hot water to the cold water in our experiment would be 73.3 degrees, but we are short. So where did that extra heat go? Well, it went a couple of places. We lost it into the styrofoam container. We lost some of it to the air. And what we're going to do now is we're going to calculate how much heat we lost. And so here's our data table again. And we have our equation. For the heat lost, we're going to find the heat we had at the start, and we're going to subtract it from the heat we had at the end. It's kind of like if you're going on a diet and you want to say, this is how much weight I lost. You would say, this is how much weight I had at the beginning, this is how much weight I have at the end, and you subtract them to find out what your weight loss was. So we're going to do the same thing. At the beginning, though, we have, at time 0, that's the beginning, we have 2 heats. We have the heat from the hot water, or the temperature from the hot water, and we have a heat associated with the cold water. So that's why we have both these terms. At the beginning, we have a hot and a cold. And then at the end, we have 2 terms, because we have 2 things. We have the hot water, the 100 milliliters, that's at 72 degrees, that's this guy. And at the end, we have this cold, which was this 72. So putting it all together, we have this equation. And let's plug our numbers in and solve it. So let's see. There's my equation. And here I go. Sorry about that. All right, Q lost equals, our mass is the mass of the hot to start. So that was 100 milliliters. C is just 1. 1 times 100 is 100. I'm not going to write the 1. The temperature, it starts at 100 degrees. We're going to add this to the cold at the start. That's this term right here. The cold had a mass of 50. C is 1. The temperature is 20 degrees. Okay. All of this minus the end. So at the end, we now have this term. The mass is 100. C is 1, so I'm not going to write it. T, that's my ending temperature. That's this number. That's 72 degrees. Plus this guy. So the mass of cold water is 50. C is just 1, so I'm going to leave it off. And the temperature of the cold at the end was 72. And so this is my ending. All right. Heat loss, Q lost, equals, I have a 1 and 4 zeros, 10,000, plus 50 times 20 is 1,000. This is the start minus the end. So I have 7,200 plus 0, 0, a 1, and a 5. Okay, so heat loss, 11,000 minus 8,700. Heat lost is 2,300 calories. All right, and the final thing we're going to do is we're going to find the percent error. And the percent error is equal to our theoretical minus our experiment divided by our theoretical times 100. So our theoretical value, when we did the math, we said the temperature should have been 73.3. We're going to subtract the experimental. It actually was 72 divided by the experimental times 100. So I get 1.3 over 73.3 times 100. Which equals 1.77%, which is actually really good. We usually like to try to be within 10%, and we are. Thank you very much. This is thermal equilibrium.